is a co-effort with Lucas van der Velde, who is a former PhD student of mine, but currently an assistant professor at Warsaw School of Economics. And this is a paper that we wanted to write for a long time, but we never had the time. Now we found the time, and it's the first public presentation. I mean, okay, it's the second public presentation, but the point is, it's a very early stage of this paper. So all comments welcome, all critical comments especially welcome, because it's a very early stage of this paper. So let me start by bringing to attention something that's super intuitive and that's super obvious, but so far has been, at least in my reading of the literature, kind of oversight, but I mean, it wasn't particularly put to the front by the economists. So the whole thing about statistical discrimination in the context of gender is that women are typically primary caregivers across society. So because of this caregiving endowment, their productivity may be reduced. So it's rational for the employers to discount that in wages. Now, that thing as a statement has actually very profound implications for what statistical discrimination may mean and what it may not mean. Specifically, it was argued before in the literature that childbearing is associated with wage losses for mothers, but not for fathers, and that fertility plans in an experimental context have been found to somehow drive or affect hiring decisions. But the point that we're trying to make is that one of the things demographers talk a lot about, and that is really important policy issue, and that everybody's having, you know, super high levels of awareness, is that we have a substantially increased age at first birth and a substantially reduced number of births per woman, which means that if you're an employer hiring a 25-year-old graduating out of university, and your expectation is that you're going to be working with that worker for the next 3 to 5 years, because that's the average duration of the first contract, then you only care about the risk of childbirth and therefore reduced probability, the reduced productivity, if that matters at all. So if the statistical discrimination argument makes any sense, you only care about it if she's going to have a baby before 28. Now, if she's not going to have a baby in expectation terms before 28, you don't give a damn, because it's irrelevant for your decision making. So delayed childbirth and reduced number of children, delayed childbirth is much more important, but reduced number of children also matters, implies that there's actually much less reason to statistically discriminate at all. Now, if you're fully rational as an employer, you're going to discount that in your discount of primary caregivers. So you should be discounting primary caregivers less. So whatever happens to social norms in the meantime, whatever happens to sharing the care and whatever other social issues there are, if the mean age at first birth goes up, if the number of births by 25-year-olds, 26-year-olds, 27-year-olds goes down, then this means there's definitely less room for statistical discrimination. But for that to hold, employers have to be A, fully rational, and B, that has to be the only reason for statistical discrimination to occur. So that's what we do. We're looking at gender wage gaps among labor market entrants. Entrants meaning the age until between 20 and 30 years of age, men and women, obviously, otherwise you can't do gender wage gaps. And we're exploring the role of delayed fertility. So we're really looking at this very narrow explanation that this is because the women can disappear because of pregnancy and child rearing. Observing demographic trends, employers should be aware that this probability goes down. So this is an implicit test of statistical discrimination, not an explicit one. This is not an experimental inquiry, but we're going to try to talk a little bit about this. Now, for that thing to work, we need to establish some sort of causal relationship between timing of fertility, so the mean age at first birth, and gender wage gap. Now, why do we look at labor market entrants? Obviously, that's where most of the action happens. Like if you care about gender wage gaps at 40 or 50, it's an important issue, but that's a consequence of what happens at the age of 20 or 25. Now, there's also empirical evidence that the entry wage is a very important benchmark for future raises, so for future earnings. So if you have a an excessive statistical discrimination at a young age, that thing is going to propagate later in the life cycle. Now, obviously, you don't have comparative measures of adjusted gender wage gap for youth, so we need to do them ourselves. For that, we collect a vast amount of data across countries and time. And because we have the data, we can also document some trends on the behavior of this variable. We provide several we propose several instruments that are supposed to help us address the causality. So going from fertility to gender wage gap, obviously it doesn't have to work this way. So the first instrument that we propose to use is the duration of compulsory education. This was explored in the literature. It has been demonstrated to affect fertility decisions, the timing of fertility decisions, and across countries and years, there has been multiple reforms to that policy variable. There's also some literature on the role of military conscription across countries. We also propose a new way to study the role of pill across countries and years. I'm going to talk more about this when I get to the instrument, but the whole idea is that there has been already substantial literature on the role of pill in fertility decisions, but this literature has usually been within one country and exploring between cohort discontinuities. We're not working this way, but I'm going to talk more about this later on. And the last one is, of course, the fertility of mothers. So a short introduction into what this paper does. I'm going to show a little toy model and then talk more about how we measure adjusted gender wage gaps, discuss identification, so go back to the discussion of the instruments, and then show the results and hopefully have enough time to summarize. So think of the super simplified, stylized version of the standard Phelps model. You have two types of workers, parents and non-parents. I don't have to call them women for everybody to understand what we have in mind. They are endowed with the same productivity, but parenthood is associated with certain productivity cost. Employers cannot know ex ante if a worker becomes a parent during the contract, but they know these probabilities and these costs. So the wages are supposed to reflect expected productivity if the employers are fully rational. And if that's the case, then we can reformulate. So exploring this definition of wages, we can reformulate the wages to express what this adjusted gender wage gap is. And adjusted gender wage gap, so adjusted for individual endowments, that's the age thing. This is simply the productivity cost weighted by the probability that you will be a parent. That's it. I mean, as simple as it gets. As I said, it's highly stylized. Now, if you take this seriously, then obviously if employers are rational, if pi goes down, and the pi is the probability that the employer will experience the worker becoming a parent, then the gender wage gap should go down. And this is the most rudimentary way to think about it. Now, why is that useful? Because if we can provide an estimate of gender wage gap, and if we can somehow provide an estimate of C and pi, we can potentially compare the two sides of this equation. So we can compare the adjusted gender wage gap with what is implied by psi and pi. And this way we can try to see if the changes in the adjusted gender wage gap in any way reflect the changes in the underlying fundamentals. Now, if they don't, there can be many reasons why they wouldn't. Depending on which one is larger, you can formulate explanations that say, if C times pi is larger than the extent of adjusted gender wage gap, then you would say, okay, employers actually overpay the parents for whatever reason. If the opposite holds, then it means that the employers do not fully account for the changes in parenthood probability and the cost of parenthood in how they discount wages. So there's something more to the story than statistical discrimination. And that's essentially the gist of the paper. So we're going to obtain the estimates of the adjusted gender wage gap from the data. We're going to characterize them. We're going to try to see if they can be, the changes in the adjusted gender wage gap can be explained by the changes in pi in a causal way. And if so, we're going to pitch one side of the equation against the other. And we're just going to try to get the comparison of magnitudes between the two effects. So how do we measure the adjusted gender wage gap? We use the super standard no-body composition. This is a useful approach to estimating gender wage gaps because it doesn't require you to make any assumptions about the functional form of wages or discrimination. It is based on exact matching, so there's no problem of comparing the uncomparable. It has been shown to be reliable even when the set of covariates is super small, because it's based on exact matching. So perhaps it's most reliable if you can't really use a wide selection of covariates. And as I said, it doesn't compare the uncomparable because by design, it's only looking at individuals who are similar across men and women in the population. We need individual data to do that. So what we do is we go out to the world and try to see what data there is. So there's a couple of sources where you can obtain something that is very generously called harmonized data. These data are not actually harmonized, but they are much easier to harmonize than anything else. So there is IPUMSI that does that, LISI, which is pretty harmonized, and then the EU provides, the Eurostat provides data for several countries and several of the member states across years. So we're using all these sources. Then in addition, there's a couple of longitudinal data that can be explored. The countries here are listed in alphabetical order because why not? But obviously these panels differ in quality in terms of sample size, in terms of frequency, in terms of detail level. You know, there is a reason why PSID is the best data there is, but it doesn't mean that the other data cannot be used. Then we also acquired a large collection of labor force survey and household budget surveys across countries. This is because if we only look at the data provided by IPUMSI, LISI, and the EU, we would have a very small selection of countries. Also because LISI, for example, even though it seems to suggest that it has a very wide collection of countries, for many countries, incomes are not reported, or incomes are not reported at hourly rate, because for some reason, LISI believed that the labor force survey or household budget survey did not have the sufficient quality to meet the LISER standards. Now, I'm not discussing LISER standards. They are obviously there for a reason, but we thought that having more countries in this collection or in this study would be of value. Hence, as you see, we gain access to countries that are typically left out of very many studies. Specifically, Latin American countries are often missing. And then the last data source is Labor Living Standards Measurement Survey by the World Bank. I'm sorry, just a second. Sorry, somebody was talking on the outside. So, so this is the big data that we have available. We needed to harmonize it. We needed to be able to define similar codification of variables. So obviously that wasn't without compromises, but this has yielded data for 56 countries that date back to early 1980s. And in total, that's about 1,200 data points. By data point, I mean country data source year. It may occur that in a given year, data for a given country come from more than one source. We adjust for that using weights. That's pretty much it. So for each of those data sets, we obtain the adjusted gender wage gap for individuals aged between 20 and 30 years. Now, this data is otherwise unavailable, so you couldn't get even raw gender wage gaps across age groups, across countries from any available data source. So that data effort was needed to obtain this specific measure. And this little graph shows you years. So each bar tells you how many data points we have in a given year. So obviously, when I say that our data starts in early 80s, do you see when I move my mouse? Good. So when I say that my data starts in 1880s, that obviously means, you know, little data, and bulk of data comes from 2000s. But at least 1990s are covered pretty richly. Now, this was pretty important because the demographic shift started in different countries in different times. So if we only look at late 2000s, then most of the advanced economies already are past the change in the mean age at first birth. These changes occurred in the 1990s. Very many countries that we call emerging economies have been experiencing this change in 2000s. So again, if we only had 2010s, that would be past this thing. But there's also a lot of developing countries and emerging economies that have not experienced the increase in the mean age at first birth. Actually, in our sample, there's quite some countries where the mean age at first birth is declining or has had the U shape. So it was first higher, then lower, then higher, which, by the way, is also consistent with some patterns of demographic transition. And this is what we obtain as the evolution of the time patterns of the adjusted gender-wage gap. Now, this graph doesn't show you much, except for the fact that essentially in every time period, in none of the time periods, we are limited to one specific data source. This is important because all of our specifications adjust for the data source and the data type. But it also shows you that there has been substantial heterogeneity in overall trends. So it's not like our results are obtained simply because there is huge, strong time trend driven on the left-hand side, and therefore the right-hand side simply adjusts. And this dispersion and the differences in time trends, this is something that makes us, on the one hand, confident that this study is not a foregone conclusion, but at the same time, it's also something that's showing that there is substantial heterogeneity in the underlying data process, which implies that there can be issues with power and so on, and having more data, more years, more countries has been of value. So this little table shows you the time trend. So this is the super simple specification where you simply put in the time trend, and in addition, you adjust for data sources and country dummies to make your time trend immune to the changes in country sample composition. And because we have the full individual data, we can compare the trends for all age groups and for the youth. And what you clearly see, and this is where our results are super consistent with the earlier literature, there doesn't seem to be a robust trend if you look at general row or adjusted gender wage gap. The coefficients here are negative, but they're not statistically significant, which is what the previous literature has found. It doesn't seem that there is strong trend across countries and years. However, when you look at young, at labor market entrants, so people aged 20 to 30, you see that there is a clear negative time trend, so that this gap has been declining over time. And this is something, and also that the decline has been of similar magnitude between the row and the adjusted gender wage gap. In the last row, we report the mean values of the row and the adjusted gap. So the row gap was about 8% and the adjusted gap is about 12%, which as an average is not that informative given the huge increase in tertiary enrollment over time. Okay, so now that I described the data, I can go more into method. So what we would like to do is we would like to estimate the following equation, where the left-hand side is simply the adjusted gender wage gap across countries and time, and the right-hand side has a bunch of controls, and the key parameter of interest here would be the beta coefficient, which links the fertility timing to gender wage gap. Now, there's obvious challenges with this. So we use mean age at first birth rather than total fertility rate, for the obvious reason that total fertility rate is perhaps not that relevant for the employers. So if I'm hiring 20 to 30-year-olds and I live in a country where fertility is postponed to 30 to 40 years of age, then I don't really care about total fertility in my country as an employer. I care about the probability that the fertility will occur before the age of 30, right? So the total fertility rate, which simply measures the number of births in a given country in a given year divided by the number of women living in that country, in that year within certain age brackets may be a completely irrelevant variable for the employers, and we actually explore this later in the paper, and I come back to that. So you would like to use the mean age at first birth, and you would be surprised to find out how difficult it is to find data on mean age at first birth. It's amazing how scattered this data is and how unavailable. The left-hand side I already talked about, so we obtain owner estimates of the gender wage gap, but the challenges to estimation are that obviously beta coefficient cannot be estimated through OLS because fertility decisions are endogenous to labor force participation, which by design is related to wages of men and women in the labor market. So you need to have some sort of identification strategy to tease out the causal effect of fertility on gender wage gap. Now, the second problem here is that there's many other mechanisms at play. I already hinted at the role of tertiary enrollment, which first of all increased incredibly over the past 4 or 5 decades across countries, and second of all has been mostly, I shouldn't say mostly, has been to a large extent driven by increased education among women. So of course countries differ in this respect. There are some countries where improvement in educational attainment has been similar across genders, but in many countries in general, educational boom has been gendered. So it was more experienced by women than men. Now that affects what the employers are expecting of the workers. It undermines the idea that age is the same, because perhaps age is the same, but the frequency of age across men and women is not the same. So that's something that may cause the results to be difficult. So how do we identify the causal thing? We propose several instruments. The first of them is compulsory schooling. So there has been prior literature that used the comparative context, so across countries and years, that shows that changing the school leaving age or changing the duration of education is causally driving fertility decisions and labor market decisions, including enrollment into tertiary education. Now, this thing usually looks at reforms within countries. So the standard way to identify is to compare cohorts that have been affected by the reform to cohorts that have not been affected by the reform. And we can't do that because we only have as much individual data as we have. And slicing that into cohorts just before or after the reform, given that most of these reforms happened in 1970s, so way before our 20 to 30-year-olds were even born, could be difficult. We could somehow try to look at their parents, but that again would be so difficult to identify. Most of the data that we were able to acquire to obtain gender wage gaps don't tell anything about the parents, so we don't even know the age of the parents in most of those data sets. So that is out of question. One thing we can do, though, is we can explore the recent changes in compulsory schooling, which were not as frequent as before and have not been as profound as before, but still there were substantial changes in how long schooling is. And you may find this ridiculous, but this data is provided by several international comparative sources, and sometimes we find this really strange. So I was expecting these estimates to be noisy, and they are noisy, but it matters. The second thing we look at is there's been literature on military conscription, which typically does not affect women, but it does affect men, and it affects the age of family formation and therefore the age of childbearing. This is nicely exogenous in the sense that nobody's ever changing military conscription laws to discuss gender wage gap, right? I mean, maybe you do something to military conscription to think about men's labor market involvement, but that's not necessarily gender equality among labor market entrants. So even if that policy is somehow driven by all kinds of social norms related to trends and tendencies that have been happening, they don't necessarily have to relate to our left-hand side variable. Now, the key instrument for us is the authorization of the contraceptive pill. I'm going to talk more about it, but the key element here is that actually whether or not you can buy the pill in a country is totally independent. I shouldn't say totally. It is not really driven let me rephrase. Of course, until the pill is authorized in a given country, you can't buy it in that country. But there's a large collection of countries where the pill has been authorized for medical purposes, but is unavailable as a contraceptive mean, or countries where, even though it is authorized as a mean of contraception, the access to it is so limited that it simply could not exist. So we are looking at authorization, which is the same thing as everybody was really interested recently, like when does EMA approve the vaccine, this vaccine, that vaccine, right? So that's an administrative procedure that countries can do. I mean, in 1960s, 70s, and 80s, they were doing it on their own. Right now, you can use supranational bodies, but essentially, it's a technical procedure that approves or does not approve that a given medicine is even available in a given country. And if you wanted to know more about this, there's actually quite extensive literature on the legal aspects of it. What we're focusing on is when this technical approval has occurred, not whether the pill is available, whether it's popular, whether it's used. We're only looking at this technical, the variation in this technical approval of pill. Now, why it matters, as if you explore the papers that I'm listing here, there's actually quite a long history across countries that none of us would suspect as we speak today, that the pill was used as medication against all kinds of medical conditions, but was not permitted as the mean of contraception. So it was approved for example, hormonal disorder, kind of makes sense, but not as a mean of contraception. It was not prescribed as a mean of contraception. It was not available for people who just wanted contraception and did not suffer from hormonal disorder. There were also other issues related to social norms on pill. So, for example, in a country called the UK, not only was it only available as a mean of treating hormonal disorders, but also only for married women. So single women could not be prescribed the contraceptive pill, even though they were suffering from a hormonal disorder. So, I mean, the access to the pill and the authorization of the pill are not necessarily the same thing, and countries really differed widely in the adoption. Now, the thing is that this authorization happens only once in a time. So we don't have within country time variation in pill authorization. And we thought for statistical reasons, it would be useful to have instruments that vary not only across countries, but also within country across time. So we're using mother's fertility. Obviously, mothers have already completed fertility, so we can look at completed fertility by the mother's generation, just to somehow relate to or tap into this idea of the intergenerational transmission of norms. Now, I talked a lot about the pill already. So the first pill was intended in 1940s. It was first approved and patented in 1960. As I said, there's substantial heterogeneity in the timing and the forms of authorization. So some European countries admitted it immediately. In some countries, there was a huge lag. Now, I can't really do a poll right now because we're having a seminar, but I'm going to give you a couple of seconds to guess which country in Europe was the last one to authorize the pill at all. 1, 2, 3, 4, 5, 10. So Poland. No.
Ireland.
Anybody else? What?
Switzerland?
Ireland.
No.
Switzerland?
No.
Malta.
No. One of the countries that we right now have is a landmark of equality, so Norway. So I'm using this example also to somehow convey that this authorization of the pill is not, it's not a way to express a social norm on women in any way. Okay, it doesn't have to be very strongly driven by that. So the timing across non-European countries doesn't vary any less than within Europe. We have a lot of those countries. As I said, admission is not the same thing as availability. Poland indeed is a great example, as all of the former socialist countries, the pill was pretty early authorized, but it was simply unavailable. I mean, you couldn't buy it anywhere. So who cares about authorization for practical purposes? Yet formally, these countries would be, as in our sample, identified as those that had easy access. Obviously, there's differences in whether the access is limited by prescription or is it over the counter, who can make a prescription, if there's any limitations on the number of prescriptions. So all these things are very specifically regulated across countries. We're not exploring that in any way because that may express social norms and political norms and all kinds of issues. We're only using the time of the authorization. What I would like to emphasize is that actually the differences in adoption are much more persistent. So authorization, once it happens, is there, right? So it's like having a new washing powder. I mean, once there's technology, anybody can buy it. Despite that fact, there's huge differences in the adoption. So this is, of course, self-reported. And I don't know if Lucas is there because I forgot the source of this data, but on average, about 40% of women in Western Europe use the pill, about 15% of women in Eastern Europe use the pill. But then in Eastern Europe, you have a small country called Czech Republic, where 1 in 2 women declare using the pill. So these things are highly specific across countries. They may also have important time variation. We're not looking at any of this. We're only looking at this authorization. So anything that can be an expression of social norms is not in our instrument. It's in all these other things that we're not looking at. Okay.
Oh, may I ask a question about exclusion restriction in this case?
Sure.
So you said it affects labor supply, which we know from the earlier research. And so it's not that it affects wages only through the increased fertility, right? It also may affect the wages because of its impact on labor supply, isn't it?
Yes, which is also one of the reasons why you're using NOPO decomposition, because we're not looking at different. So if there's any type of women that don't participate in a labor market for whatever reason, based on the covariates that we can identify, so only on observables, we're definitely not including that in our measure of gender wage gap. So this is as good as we can get to this identification. Okay, so essentially this is, as I said, an IV specification with several instruments. The mean age at first birth, the MAB, is instrumented with the pill, which has no time variation, the education or the duration of education, the duration of schooling, which has both time and country variation, the conscription, which has both time and country variation, and mother's fertility, which has both time and country variation. Now, you may read here that the pill states I and T, where I states the country and T states the time. And this is because what we do is for each birth cohort, we compute how many years have passed since the authorization of the pill. Now, we don't have to do it because we're using a Baltagi instrument or a Baltagi specification of the instrument. So I'm going to discuss this in a short second, but it's just so much easier to estimate when there is this thing. And obviously the T component on the pill is just deviations from general time trend across countries. So this is just country-specific time trends. That won't affect our specification. It would be important for the interpretation of the first stage, but it's not really relevant for the interpretation of gamma in the IP specification. So what does this Baltagi instrument really do? The Baltagi instrument decomposes all the first stage variables into time variant and time invariant. And each variable is then represented in 2 variables. So each instrument is represented as 2 instruments. One is the time varying component of that instrument, and the second one is time invariant component of that instrument. Now, obviously, this instrument or this way to estimate two-stage d-squares was not designed for the type of estimation that we have here, but it performs quite well. It fits. We adjust standard errors for the fact that our panels are unbalanced, and that's as good as we can do with this stage. So where from do we take all this data? So for the mean age at first birth, we go to Eurostat and the United Nations Agency for Education. They provide data for the industrialized, developed, rich countries, but are really bad at other countries, and especially are very bad at long history backwards. So we also use human fertility database. This is helping us with a number of countries. But other than that, we really had to go through websites of the central statistical offices across countries, trying to find their annual demographic report or whatever, decennial demographic report, and just look at the data that they report. For many countries, this was unavailable. So one example of a country for which you have that totally unavailable would be China. But there's one paper that reports data for 10 years. I actually wrote the authors of this paper and asked them if there's like earlier data or later data, and they say no. I don't know how that's possible, but apparently they only have data for this specific 10 years between whatever, 96 and 2006. So for many countries in our sample, we were able to acquire data simply going over papers and trying to find if somebody has used DHS data or some other data source to compute mean age at first birth for those nations. This is also an important limitation for how much we can use our individual level data on wages. We could potentially have more countries, but their data on mean age at first birth is simply unavailable. This is particularly true for Latin America, by the way. So the pill data come from a paper by Finlay, Cunning, and Pohl. The military conscription come from Mulligan and Schleifer, and their data ends, as you can see, in 2004. But they are kind enough to say where from they were taking their data. So we went to Military Balance, which was the original source, and updated their data to cover the years and the countries that they have omitted. The compulsory schooling data comes from UNESCO, but this data doesn't cover 1980s. For this, we used a couple of papers that are listed in our paper, but I skipped them for the purposes of this presentation. And for the mother's generation, thank goodness we can use a simple source called the World Bank, and they simply provide completed fertility across countries and years for like one generation older individuals. So here go the results. How am I doing with time? I should be finishing, so I'm close to finishing. The really important is just the first row. So 1, 2, 3, 4, these columns are only different by which instruments are included. The which instruments are included are in the bottom row. So in the first column, we report all 4 instruments at the same time. And second column is just compulsory education and military service. In the third column is just a pill. And in the fourth column is just the mother's fertility. Now, what these results show is that there is not much difference on which instrument composition you're using. You get pretty much the same results. Now, these results are also similar in magnitude to the results that would have been yielded by a simple OLS. 2 ways to look at this. One way, you really have poor instruments. You're not doing any causal identification. You're just thinking you're doing causal identification. So that's the bad interpretation. The good interpretation, the bias that is from endogeneity is really small. So one thing we can do is we can try to provide an analog of the F statistic for the weak instruments. So that's the F statistic row in this table. Now, obviously, simple F statistic for this type of estimation doesn't exist. So one of the reasons being that, as I said, there's 2 instruments for each instrument, time varying and time invariant. And so this F statistic is overstated for that very simple fact. But even if it's overstated by a factor of, say, 10, it's still big. So it doesn't seem like we're suffering from weak instruments, but it does seem that either the bias was not very small or the instruments are not that powerful in accounting for endogeneity. Now, as I said, we're also looking at alternative measures of fertility. So the first 5 columns all look at young generations, so 20 to 30-year-olds. Measure of fertility is mean age at first birth, and we're looking at the adjusted gender weight gaps. Now, in the last 2 columns, we're looking at youth and all, but instead of looking at mean age at first birth, we look at total fertility rate in a given year in a given country. And as you can see, the estimates completely disappear if we look at all birth cohorts. If we stick to younger, so the column 6, the coefficient is there and it's statistically significant, but it's so large that I find it very difficult to take it very seriously. Now, one last exercise that we do to try to discuss so let me just interpret this number. So what does this 2.6 mean? This means that if the mean age at first birth goes up by 1 year, which by the way is a lot, then the adjusted gender wage gap declines by 2.6 percentage points. Now, is that a little or a lot? You may recall that the mean adjusted gender wage gap in our sample was about 12%. So that would be 1/4 of the total level effect. So that would be a large coefficient. This is also one of the reasons why I find it really difficult to believe this coefficient. But there's also other problems with this OLS specification. And one more exercise that we do is we try to compare, as I said, so these are the specifications you know already. It's column 5 and 1 from this table. But in addition, we provide the estimates on row gender wage gap and total fertility rate for young and for everybody, and there's no effects there. So this is really about quote unquote discrimination. So the adjusted gender wage gaps for rows, there's nothing. And it seems to be much more about the mean age at first birth than about total fertility rate per se. Now, is this little or small? Let me remind you of our simple toy paper. So the left-hand side is the adjusted gender wage gap. The right-hand side is what it should be. So what we're going to try to get is the measures, proxies, whatever you want to call it, of C and pi, and compare that to the estimated gender wage gaps. So the pi is the easy one. For some countries and years, you can obtain age-specific fertility rates, which means you can easily integrate the probability of getting any kid, first kid, at least one kid, between the ages of 20 and 30. And so you can take the 1 minus this thing, and that's the probability, you can get the probability measure that somebody gets, the woman gets a child between the age of 20 and 30. Not for all countries, but for some countries you can use age-specific fertility rates. Now, what do you do with the cost? So far, we're working with the time-use data from the ISSP, and we're doing kind of difference in difference thing. So the ISSP asks people how much time they spent on different types of activities in the past week, and people report that in hours. And in this formula, if it says M, it's a man. If it says W, it's a woman. If it says K, it means with children. And if it says tilde K, that means without children. So what we're looking in the data is the change, so the difference in the mean or median time spent on caring, that's the small cap t, between men and women with and without children. So essentially what we're looking at is how much there is a change in time endowment for women who have children relative to women who have no children, and how this change in decline in time endowment is different from analogous change for men. Okay, and that's our proxy for C. Now, you don't have to criticize me for using ISSP rather than time-use data. I'm very happy to discuss why I'm not using time-use data, but it's just a proxy at this point. And this is difference in difference. So think about it as time endowment. Everybody has some time. I don't know if you can see both of my hands in the camera, but everybody has some time. So we're cutting down parts of this time endowment for whatever caring activities that people have. They don't have to be related to children. They can be caring for other people in their household or whoever. So then we're looking at this caring for men and women with and without children. And we're simply taking the differential effect that women have on their time endowment relative to what men have on their time endowment. Okay, and we're adjusting this thing for the probability that they have children. And that's what you see here. This is a zoom, a very badly done one, but as good as I could. internet problems. So this thing here, I'm just going to show you how to read the graph, and then I show you all the results. So this thing here is the estimated gender wage gap for Austria. Austria, because it's the first letter of the alphabet A, that we were able to get both data on time use and age-specific fertility. So this is estimated because it's from our samples. So for that same year for which we have availability of the ISSP data, we are doing an estimation what will be the adjusted gender wage gap in Austria in that year, okay? Losing all data that there is. Then the triangle tells you what's the simulated C times pi. So this what the average adjusted gender wage gap should be equal to if we use the mean reported carrying time. And the green rectangle tells you the same thing, but in addition to carrying time, we also include household chores. Okay, so the ISSP reports all kinds of time use variables. So there's carrying and there's household chores. So in the C, so decline in time endowment, we can include only carrying or carrying and chores. And so as you see in Austria, the estimated adjusted gender wage gap will be about 10%, plus or minus 1 percentage point. Then at the simulated at the mean, so C times pi, that would be about 15%. And if the C adjusts for chores, not just carrying, that would be about 22%. Now, this is for all the countries for which we were able to get that. So that's why I said the previous one was a zoom. This is a bit smaller, but I hope you can still see well that there are some countries in which the implied C times pi is much lower than the estimated gender wage gap. So best example here is Germany. The implied C times pi would be about 5%, whereas the estimated gender wage gap is about 12%. And that's an example of a country where there must be something else behind gender wage inequality. It simply cannot be estimated by the current risk that a woman becomes a parent, differentially between, all this stuff. So either employers in this country are not fully reacting to the changes in fertility patterns, which means they are not rational. So statistical discrimination argument based on rationality of employers requires rationality of employers. And if they're not rational, it simply cannot work. Or there's other reasons, such as non-statistical discrimination. Right? But there's also other countries. The Austria was one of those examples, but let's just drop Austria for a second. Let's just look at, and Great Britain is another example of that. But let's look at our favorite country, Poland, where you see that the estimated gender wage gap potentially encompasses the pink triangle, which only looks at the carryings, but it definitely doesn't encompass the square, the green square, which is not only carrying but also chores. And this, perhaps encompasses means, it's at the top of the whisker. So, I mean, it falls within the confidence interval, but it's not really properly there. Hungary is another example where the square is much above the estimated effect for the gender wage gap. We also do one more experiment where instead of mean, we use median. So that's the next slide. So the pink triangle is the same as it was before, but right now, instead of the green rectangle, we have a blue rotated rectangle. This looks at median rather than mean to adjust for potential, skewness of distributions and all this stuff. So Austria is still much more equal than it should be. Germany is much more unequal than it should be. France is much more unequal than it should be, right? But interestingly, the UK, which was much more unequal than it should be, becomes equal when we look at medians rather than means. So that hints that potentially the employers are actually adjusting their expectations, but they are not rational expectation optimizers in the sense that they don't look at the mean, they look at the median of the distribution or something like that. I mean, just thinking about. So let me summarize because I'm over time. One of the questions that has been out there a lot is that we kind of think that whatever scope of gender inequality there is, it's because women are somehow bound to be primary caregivers, and because of that, employers are fully rational to discount that in wages. Do we find confirmation of that hypothesis? Tentatively, yes, in a sense that delayed fertility among youth is associated with a causal decline in adjusted gender wage gap. So part of this information that is hidden in the fact that mean age at first birth goes up is discounted in lower gender wage gaps among women. As I said, we get this result on a sample where in some countries mean age at first birth doesn't go up, or there's a U-shape or whatever, and we're still finding this result. The estimates of about 2 to 3 percentage points say that this is about 20 to 25% of the total effect. So that would be pretty large. They are pretty stable in terms of magnitude. They're pretty robust across model specifications. So this is all reassuring. The problem, of course, is that IV and OLS are similar, but our F statistics are pretty strong. So if you take them at face value, as we can compute them here, then maybe this is convincing. Now, the benchmarking exercise that I just showed on a previous slide, it shows that C times pi explains the average gender wage gap only sometimes. So in some countries, it seems like the inequality in the labor market, as we are able to estimate it, is consistent with rational employers statistically discriminating against parents. But this is only true for some countries, not all. And there's quite a large selection of countries that we were able to find in this small search of age-specific fertility rates availability and timeless data availability, for which we could obtain this C times pi, where this signal doesn't seem to be correctly received.